Okay, I guess we can start. Hello and welcome the participants of European Non-Associative Algebra seminar. It is my pleasure to introduce today's speaker, Zahra Nazemian from University of Graz, Austria, and who will be talking about Aut-stable subspaces of algebras and beyond. Please, Zahra, you may start.
Thank you so much. Thank you for very correct pronunciation of my name. And so I would like to thank the organizers of this weekly seminar, very nice seminar, in particular, Ivan, who invited me. And I also would like to invite all of you for submitting your good papers to the new established journal of Non-Associative Structures. As one of the editors, I know that the goal of the team of Ivan and the people who established this journal is just accepting very good papers. So please submit your good papers here, and you will never regret, because it's we are very strict. So, and what I present today is somehow a summary of some works, which is joined with several people. With Demir, he is now in Turkey. He is actually a bachelor student, and he was my somehow exchange student during a program for a couple of months. And also Nina Gupta. So maybe I should. Nina Gupta, he is in India. And Huang, he is a professor in Shanghai University. And also Yanhu Wang, she is also a professor in Shanghai University. Xingting Wang, he is professor in United States. And Xin Tang, he is a professor in the United States. And James Zhang, a professor in Washington University, Seattle. Actually, he was our leader somehow, and I'm grateful of him because he involved me in this sort of questions and research. And here are the papers that I give you a little bit about some of them. So relative cancellation, it is already accepted in Proceedings of American Mathematics Society. And the Aut-stable subspaces of Grassmann algebras, this is joined mainly with Demir, and it was accepted only 2 days ago. Also, the work with Nina, it's in progress, and the paper with my co-authors, as you can see, Dixmier property for Poisson algebras. This one is already in archive. We submitted only last week, and universal homogeneity, which is in progress. So what is the common, the intersection of these works is using the concept of Aut-stable subspaces to approach some questions and challenging problems. So our story starts with Kraft. He is retired professor in Switzerland. In 1996, he had a talk in Bourbaki seminar, and there he listed 8 challenging problems on affine spaces. And there is also a paper written exactly based on this talk, and the same title, Challenging Problems on Affine Spaces. And as I told you, there he lists 8 challenging problems. To understand the problems, I just fixed the notation of automorphism. I need this definition. So all the rings here are associative. So a morphism from A to B, when A and B are C algebras, is a map that respects our operation. So we have two operation, yeah. So one is multiplication, one is addition, yeah. So f should respect the multiplication. That means f of product of two elements is product of f of that elements. Also, f should respect the sum of elements, yeah. So f of a1 plus a2 is f of a1 plus f of a2. But A and B are C algebras. So what F does over C, elements of C, and because A and B are C algebras, so they contain C. So F of an element in C should be equal to C. So this is the definition of C algebra morphism between two algebras. Okay. And what happens if the kernel is 0 and the image is whole of B? Then we call it an isomorphism, yeah? And an isomorphism from A to A is called automorphism. So this is the thing that I need, the definition of automorphism of A. So A is a C algebra. Good. So what is the first challenging problem that Kraft lists? He said, what are automorphism of polynomial rings with n variables? So the simple question, but difficult to answer, yeah? So from his point of view, this is one of 8 challenging problems. If I want to tell you what is done, the case n equal to 1 is easy, because when you have a polynomial ring with one variable, let's say of x, then it's really easy. You can check that every automorphism here in C of x is actually something that takes x to ax plus b, where a and b are in C, but a is not 0, and b can be 0 or anything, yeah? You can check that the automorphism of C of x are exactly these things. So nothing else can happen. So in this case, we are done. But when when n is equal to 2, this is difficult to explain what exactly are the automorphisms, but it is not known, yeah? So this is done in the work with Heinrich Jung in 1942, but it's complicated to explain here. So the question is open for n bigger or equal to 3. Of course, we know some of them, but the question is, what are, can we describe them, all of them or not? So this is one question. And the second question that he says, this is one of 8 challenging problems, is giving a algebraic geometric characterization for polynomial rings with n variables. So what does it mean? That means give me a nice characterization that if I look at any ring, any given ring, I can tell you if it is polynomial ring or not. Yeah. So why it is important? For example, this ring, this is Russell cube, and for a period of time, it was a problem to see, or a challenging problem to see, if this guy is a polynomial with 3 variables or not. Yeah. So because there was enough somehow evidence to see if it is polynomial, but at the end they understood it is not. However, so having some nice characterization is very important. Good. So I'm not going to list all of 8 challenging problems, and this is the last one. So also Zariski cancellation problem. So he asked, this is also, I mean, I think this is well known for many of us, but he says that is a polynomial ring with n variable cancellative or not? So what does it mean? That means that suppose I add one more variable to this polynomial ring with n variables, so I have a polynomial ring with n plus 1 variable. And suppose that this happens, that this guy, the new guy, is isomorphic to b of x, so b is any C algebras. And so polynomial rings over B with one variable x. Suppose that this happens. Now can I delete x and say that, okay, B is isomorphic to the original one, polynomial rings with n variable, or not? Okay, this is also challenging. If I want to tell you what is essentially done, let's look at the little cases, n equal to 1, 2, or 3. For n equal to 1, they could understand it quickly in 1972. Polynomial rings with one variable over field K. So now instead of C, I wrote K. So K is any field, any characteristic, any property. K of X is cancellative. So it has a Zariski cancellation problem is done for case n equal to 1. And for n equal to 2, it was done during 3 works. So for any field K, so in this case also the situation is done. And finally, after a long time, for n equal to 3, Nina Gupta, she is an Indian mathematician, she could observe that if the characteristic of our field K is non-zero, then for n equal to 3, our polynomial rings with 3 variables over our field K is not cancellative. So this was somehow breaking news, and but for characteristic 0 and n equal to 3 or more, everything is open. Okay, what is the goal of this talk? So I want to approach some of the questions using the concept of Aut-stable subspaces. So I need to tell you what are Aut-stable subspaces. If you haven't seen it before, look at this rotation of these 2 flowers. So you see the star is on one of the leaves, and I rotate these flowers. It's somehow like I'm doing an automorphism. But if you look at the center is always there, yeah? So it is, I want to tell you what's the definition of Aut-stable subspaces somehow informally. So formally speaking, suppose that you have a K algebra. So K is a field, A is a K algebra. It can be commutative, non-commutative, or anything. And so when A is a K algebra, A is also a vector space over K, yeah? And you can look at A as a vector space, and you can think of its subspaces. So you forget ring structure. You look at it as an abelian group with addition that we have over A. A is a vector space. And take a subspace V of A. Yeah, so V is called Aut-stable if it is stable under any automorphism. So automorphism of A. So what does it mean? That means that f of V is always inside V for every algebra automorphism that we defined in the first slide of A. Yeah. So F is an algebra automorphism. Okay, so for any algebra, K algebra A, I can find immediately Aut-stable subspaces. So because 0 is always a subspace which is stable, right? Because f of 0 is always 0, so we are done. And also A itself, yeah? So if I take V equal to A is Aut-stable, no? Yeah, because f of A is always equal to A, yeah? Good. Another example, which is trivially we can say it is Aut-stable, is our field K, because K is equal to K times 1, so it is a subspace of A. And it is Aut-stable because we set the definition of automorphism, the constant elements of our field goes to the set. Yeah, they are fixed. So 0, k, and a are trivially, or we call it them trivial Aut-stable subspaces of A. Good. So the example, the interesting one, or a non-trivial one. So, okay. So, what are Aut-stable subspaces of polynomial ring with one variable? Because we know now what are automorphisms. Yeah. With one variable, it is easy. Actually, you can find infinitely many Aut-stable subspaces because we know what are automorphisms, and for every integer m is an integer number bigger or equal to 0, you can see that if v of m is the set of all polynomials of degree less or equal to m, then this v of m is actually a subspace of c of x. And it is not really difficult to see that v of m is Aut-stable. So in this case, when we have only one variable, we have infinitely many Aut-stable subspaces. So, but we will see that something very interesting happens when we increase the variables. There is no question so far. I go ahead. Okay, so let's see what are connected graded algebras, because I need them to give the characterization for polynomial rings. When you have an algebra A, so A is a K algebra. A is K can be any field. A is called connected graded if you can find such a decomposition for A. So A is direct sum of AIs. I is bigger or equal to 0. What are these AIs? AIs are just subspaces of A. So we look at A as a vector spaces over K. So they are just subspaces, but we are working with an algebra, so we can multiply elements, and this should happen. So AI times AJ should be inside AI plus J for every I and J. And because I wrote connected graded, that means that A0 is equal to K. So this is connected graded. What are examples? Here I wrote one example, but you will see another one. Polynomial is with n variable. This is clearly connected graded. So each AI you can put homogeneous elements of degree exactly I. Good. So let's try to answer the question, the characterization problem for polynomial rings. Yeah, it was, I think, the second question of the craft. Yeah, so with my coders, as you see here in this work, relative cancellation, we could see that if you take a C algebra, this is also true for any algebra, K algebra, which is of characteristic 0, and algebraic calculus, but here I wrote only for C algebra because this is the answer to the question of that. A C algebra A not equal to C is isomorphic to a polynomial ring with n variable when n is bigger or equal to 2. As you can guess, if and only if the following two conditions hold. First of all, A doesn't have any non-trivial out-stable subspaces. So you see, when n is bigger or equal to 2, our polynomial rings with n variable doesn't have any non-trivial out-stable subspaces. This is in case we don't know what are all automorphism of polynomial rings in general. Okay, I have also another condition, and A should be a finite generated connected graded algebra. So this is also necessary. Why it is necessary? Because because in the theorem I didn't write any condition that if my ring A is commutative or non-commutative, anything. So if you take the Weyl algebras, they are non-commutative rings. They satisfy condition 1, and they are of course not polynomial, first of all, because they are not commutative. And so in general, I cannot delete condition 2. Yeah, so it is necessary. And okay, if you maybe I should recall the definition of Weyl algebra. Weyl algebra is just the quotient of free algebras. For example, if we work with Vn, Wn, the nth Weyl algebra, we have a 2n generator here, x1, y1, x2, t2, y2, and xn, yn, and the modulo relation. Yeah, so I is our relation. I don't write all the relation because it's too much, but I say because it's easy. So all xi should commute. So here xi, xj is equal to xj, xi in Vn. Also, all vi is yi is commute. So, for example, y1, y2 is equal to y2, y1. What about the relation between xi and yi's? Xi and yj, when the index are different, they commute. So xi yj is equal to yj xi. But because the ring is not commutative, we have a relation that doesn't commute, and this is the case with when xi and yi. So the index are the same. Yeah. So xi yi is equal in Vn. So is equal to yi xi plus 1. Good. So you see, this is the ring very close to commutative, but it is not. And about, you may ask, what happens if I put the condition commutativity here? Can I delete the condition 2 or not? Can I say a commutative algebra not equal to C is isomorphic to polynomial with n variables if and only if it doesn't have any non-trivial out-stable subspaces? This is our question. This is a conjecture, so that we think should be, I don't know. So when it's conjecture, I don't know if it's true or not, but we have a good candidate that we are working on it. So, but till now, I don't know really that at the end, this guy, so this is the coordinate ring of SL2. It's quite well-known algebra, but it's very difficult to see if it has non-trivial out-stable subspaces or not. So we know this is not polynomial ring. But the problem, at least for me or for us, it is with Neha Gupta, is that we couldn't see the characterization of all, automorphism of this guy. So this is challenge. We have some, we can find some automorphisms, we are working with them, but we don't know all of them. At least for me, it seems it is open. Okay. I cannot give any other answer to the question of the 3 questions of Kraft, but I would like to say that maybe out-stable subspaces help to work on the Zariski cancellation problem, because if you look at this Russell cube, okay, we know it is not binomial ring, and the interesting thing is this, that it has a non-trivial Aut-stable subspaces. And maybe for people who are familiar with this area, it is actually the intersection of kernel of all local nilpotent derivations. So that one is non-trivial Aut-stable subspaces. So we know it's not polynomial. But what happens for A of x? So look at the polynomial rings with one variable over A. We don't know if this is polynomial or not. If one proves that this is a polynomial ring, then he or she has solved the C cancellation problem. So maybe just because our work is new, maybe just one as an application, one can try to see if this guy, polynomial is with one variable over A, this is the Russell cube, has or doesn't have any non-trivial Aut-stable subspaces. For sure, this is very useful. I don't say it is something easy or it can be done, but this could be a good idea. Okay, so let's go to Grassmann algebras, because they are also very close to be commutative, and actually Kunulab Demir wanted to work on these algebras. And I also attended one of the talk of this seminar. It was about Grassmann algebras. I really learned a lot of things. So I said, okay, they are new to me, but let's work on them. Because they are very close to commutative binomial rings, we said, okay, let's see if what are the Aut-stable subspaces of these rings. So what are Grassmann algebras? If you attended the talks before, you know it. I just recall it. So it is the algebra generated by n variables. Here I wrote E1 till En, but you can think of X1 till Xn if you want. And the difference is that so instead of commutativity, you have anti-commutativity. So EI EJ is equal to minus EJ EI. This is the relation that you have for every I and j between 1 and n. You can see immediately what happens if I take I equal to j, then EI square is equal to minus EI square. And so 2EI square is 0. And if my field is not of characteristic 2, I can conclude that EI square is 0. But if my field is of characteristic 2, it is known that this Grassmann algebra is just the commutative ring that we know with n variables. Commutative polynomial rings. Good, so I told you if the characteristic is dot 2, then EI square is 0, and this is very useful, and this is telling me that I can give a nice grading to my ring epsilon, the Grassmann algebras. So it is equal to K direct sum epsilon 1, epsilon 2, blah, blah, till epsilon n. So this n is exactly the number of my generators. But what are these epsilon i's? And epsilon 1 is just the vector space generated by EIs. Epsilon 2 has two generators, so this is generated by elements in form of EI, EJ. And you do the same at the end. Epsilon n is just generated by K E1, the product of E1 till En. You don't have any other option because epsilon I square is 0. And this is very useful. So this is finite and very nice. So as you see now here, epsilon is connected graded. If you remember the definition of connected graded algebras. And we know it is not commutative. So this is telling us, because of the theorem, we know this is not polynomial rings. So when the characteristic is not equal to 2, so this is telling us that epsilon, of course, has Aut-stable subspaces. Yeah, non-trivial Aut-stable subspaces. So the question that we had, what are exactly? And here is the answer. So when the characteristic is not equal to 2, yeah, the field is not of characteristic 2, we can see that B subspace of epsilon is Aut-stable if and only if B is one of the following forms. So B is direct sum of epsilon k's. K for you have a J. So the form A says that, okay, you have a J between 0 and n, and bigger than 0, non-zero. And B is direct sum of these epsilon k's, but all even ones. So K is even between J and n. For example, if I take J equal to 2, B is equal to epsilon 2 direct sum epsilon 4 direct sum epsilon 6 until I get to the even. If n is even, then I have it. If not, the one before it. Also, so for J equal to 3 also, J equal to 1 also the same, because epsilon 1 is not counted, yeah, because I need the even one. So this is either in this form, or I can find J, again, non-zero. But this time, B is direct sum of epsilon k, but all of k, bigger or equal to J. You can see they are different, yeah? And the other, I have two other forms, but they are very easy because they are, the part C is something which can be sum of one in form A and sum of one in form B. Yeah, if I sum them, they can be in none of the above forms. So part C says that, okay, our B, the Aut-stable subspace, is sum of something in form A and sum of something in form B. So you see, B1 plus B2. So the last one, as you can guess, is when I add K, because the K is not here. You see, our K didn't appear here. And we are fine because we are looking at stable subspaces, not algebras. So the last form says that add K to any of the above forms. Again, you have Aut-stable subspaces. So the last form is B is equal to K direct sum B prime. So B prime is either in form A or B or something C. And good. So I don't know if there is any question. If not, I'll go ahead. The last part that I want to talk about it is Dixmier property for algebras. Here, the use of Aut-stable subspaces are hidden in the proofs, and it's complicated to tell you, and the paper is just submitted last week, so I wanted to tell a little bit result about it. But if you found it interesting, you can look at this video of my colleague, Shin Tang. He had a talk in December, 1st of December, 2025. And the video is available. and he talked about 1 hour or more about this work, very complete, and goes introduce all the complicated conjectures that I will mention to it very quickly. But to find the talk, you may search this title here, Revisiting Fundamental Problems Workshop. So it was really a workshop about important conjectures, and as you see, it was December 1st till December 5, and he explained that very good. So, but what is the Dixmier property for algebras? Here, for the last part of my talk, K is algebraically closed speed of characteristic 0, just so everything works well. And Dixmier property says that, or asks that, if you have a Poisson K algebra A, so you have a K algebra, this is commutative, so we are happy, and you have a Poisson bracket on A. What does it mean? It is a Lie bracket, and you have Leibniz rule. So this is just definition of I give you a Poisson K algebra A. Then A, this is not our definition, it was done before. I am just recalling. A is said to satisfy Dixmier property if for every injective Poisson K algebra morphism F from A to A. So this is an K algebra morphism, like we defined, but this is a Poisson morphism. That means that if, okay, it's algebra morphism, it should respect multiplication, addition, or so on, but it should also respect the bracket now, because we have a bracket on A, the Poisson bracket. So f of bracket of A and B should be bracket of f of A and B. So I think I have a question in the chat box. Aut-stable subspaces can be called characteristic. I don't know if there's any work that they say characteristic, but I would be interested to know more. Okay, so if every injective Poisson K algebra morphism is a bijective, so it is automorphism. Yeah. So if this happens, so you say that the K algebra, the Poisson K algebra, has Dixmier property. So every injective Poisson morphism is bijective. If this happens, you say A is Dixmier, has Dixmier property. Why this example, this definition felt interesting? Because Poisson conjecture. So Poisson conjecture, I'm not explaining this conjecture, and I am just recalling them. Poisson conjecture says that but it seems they are very important conjectures. The Poisson Weil algebras Pn have Dixmier property. So Poisson algebras are always commutative in this setting here, but we learned what are Weil algebras, yeah? But this is nothing to do with Weil algebras. This has its own definition, but if you see the definition, it is somehow, you see why it is called Weil algebras. The Pn is, okay, it's commutative polynomial rings, but Pn has 2n variables. So polynomial rings over these variables over our field K, but with these variables x1, y1, x2, y2, and xn, yn. Okay, what is the bracket? Bracket, if you see the bracket, you recall Weil algebras, because the bracket of xi and yi is equal to 1. Other places they are 0. And the Poisson conjecture says that, okay, if this Pn has Dixmier property or not with this Poisson bracket. And Poisson conjecture is somehow equivalent to Dixmier conjecture. Dixmier conjecture says that every endomorphism of a Weyl algebra is the non-commutative one is bijective. Yeah, and these two conjectures are known also somehow stably equivalent, but I would say here equivalent to the Jacobson conjecture, which is famous. Yeah. Okay, so we are nothing to do with these difficult conjectures, but we work with this Dixmier property A. And I would like to tell you one important example that my co-authors, this is not mine, considered. They looked at P omega minus Kesu. So suppose that A is the polynomial is with three variables, X, Y, and Z. So A is this guy. Omega is an homogeneous element in A. We are going to give a Poisson structure to this commutative algebra A using omega. So I need to say what is the bracket of X and Y, what's the bracket of X and Z, and so on. So it's enough to look at this. So the bracket of X and Y is defined to be the partial derivation of omega with respect to Z, which we call it omega Z. You see, because Z was missing, you can just remember by this way. And bracket of Y and Z is defined to be omega X. And the bracket of Z and X is just defined to be omega Y. Good. You may wonder if we have an easy formula to say what is the bracket of F and J. And yes, this is equivalent to say that bracket of any F and J in my polynomial is equal to determinant of this matrix. Yeah. And what important is here, you can see that if, for example, here instead of G, I write my omega, and then the second row and the third row are equal, so the bracket is 0. This is telling me that omega is in the Poisson center of my algebra. So I can consider a quotient of A, which is again the Poisson algebra. Okay, so they write A omega to just recall that, okay, we are giving a Poisson structure to A using omega. So they use this notation to just be easier. And omega is called the potential of A omega. And I told you they are omega is in the Poisson center, and for every Kesu in K, we can define the new Poisson algebra because omega minus Kesu is also in the center. So it is the homomorphic image of A omega, but generated, but I mean, in the quotient, I have this ideal generated by omega minus Kesu. And we say this omega is has an isolated singularity if it has only one singularity is in the origin. That means that this ring is finite dimensional. So A over the ring, the ideal generated by omega X, omega Y, and omega Z. If this guy is finite dimensional, because it has isolated singularity. And okay, what the important result of my co-authors, as you see, their name, this is not my work, but it is a very groundbreaking work using techniques and valuation by valuation techniques and very technical works, they show that this P omega minus Q under some condition is Dixmier. So what is the main result of them? They say, suppose that the degree of omega is bigger or equal to 5, and omega has our property that I just told you. It has isolated singularity. Then they prove that P omega minus Q has the Dixmier property. But P omega minus Q, they also prove in their papers that it's a domain. And so we can look at the quotient field of it. And it's also known that we can extend the Poisson bracket on this P omega minus Q to the quotient field. They prove even that this Q of P omega minus Q has the Dixmier property. And another thing that they do, they look at the set of all Poisson algebra morphism of P omega minus epsilon. And also the same for its quotient. And they prove these two sets are equal. That means anything here can be extended there, and also the restriction works well. And this two set are finite and bounded by a number that you can see here. But what we did, when I joined them, we tried to extend these results to the tensor product of these P omega minus Q. So we asked what happens because P omega minus Q is the quotient of a polynomial with 3 variables, so it's generated by 3 elements. But it would be nice to have more examples of Dixmier with Dixmier property with generators are bigger than 3 elements. Yeah. So what happens for the tensor product of them? So we could prove that this guy has the Dixmier property, but they have some conditions. These omega i's that you see, they are all potential. So the degree of all omega i's are all bigger or equal to 5. The degree of any of them are different. And they have isolated singularity, so they have all these conditions. So if the degree are different, 2 by 2 different, and then we could see, okay, the tensor product, of course, of K is Dixmier. And also, this is a domain, because our field is algebraic equilibrium, if you remember, characteristic 0. Then the quotient field is also Dixmier, so this is also nice. And we also look at the automorphism of them. They are again finite. And we gave also a bound during the proof, but it's not written here. And what I can say as a last thing is this, that we also know when P is Poisson simple. I mean, the tensor product of these guys, if and only if all EIs are non-zero. Yeah. So by this result, I finished this work, but I would like to tell you that in the proof, again, we used the concept of Aut-stable subspaces. This is the reason that I added this work also to this presentation. And so I finish here, and thank you so much for the attention.
Thank you for your interesting talk, and I think now it's time for questions. So if anyone has any questions, feel free to ask. Okay, if there are no questions, then once again, thank you very much for your detailed and interesting talk. and see you everyone in next week.
Common. So the groups with Dixmier property are called co-Hopfian. I have worked with co-Hopfian models, so it's very nice to see them. So I will search for some references. Thank you.